Your analogy to solving equations like a plus b equals c is a valid way to think about how training deep neural networks works, especially in the context of supervised learning tasks. Pradeep K. Suri, author and researcher. In supervised learning, A corresponds to the input data, features. B corresponds to the model's predictions, output. C corresponds to the ground truth or actual target values, labels. During the training process, 1. The network starts with random initial weights and biases, so the predictions, B, are far from the actual targets, C. 2. The network adjusts its weights and biases, parameters, using optimization algorithms like gradient descent to minimize the difference between the predictions, B, and the actual targets, C. 3. The loss function, a measure of the error between B and C, is minimized as the weights and biases are updated iteratively. 4. As training progresses, the network's predictions, B, get closer and closer to the actual targets, C, just as you would iteratively adjust A and B to satisfy A plus B equals C. So, in essence, training a deep neural network involves finding the optimal weights and biases that allow the network to approximate the desired mapping from inputs, A, to outputs, B, such that the error, difference between B and C, is minimized. This iterative optimization process is similar in concept to solving equations in mathematics. You're correct that understanding the values of variables like A, B, and C is crucial when working within specific domains or contexts. The values of these variables represent data, parameters, or quantities that are central to problem solving within those domains. Here's how the importance of these variables can vary across different domains. 1. Mathematics. In pure mathematics, the variables A, B, and C often represent numbers or mathematical entities. They are essential in equations, inequalities, and mathematical expressions. For example, in the quadratic equation x2 plus bx plus c equals 0, the values of A, B, and C determine the roots of the equation. 2. Physics. In physics, these variables can represent physical quantities such as distance, A, velocity, B, and time, C, in equations of motion. The values of these variables play a fundamental role in describing and predicting physical phenomena. 3. Engineering. Engineers frequently use variables like A, B, and C to represent parameters in design equations. For instance, in electrical engineering, A might represent resistance, B could stand for capacitance, and C might represent inductance. 4. Finance. In financial modeling, A, B, and C can denote various financial parameters. For example, A might represent the initial investment, B could be the interest rate, and C may represent the time period in financial calculations. 5. Programming. In computer programming and software development, variables with names like A, B, and C are used to store and manipulate data. Their values can represent anything from user inputs to intermediate results in algorithms. 6. Statistics. In statistics, A, B, and C often represent variables in equations or statistical models. For instance, in linear regression, A represents the intercept, B denotes the slope, and C is the error term. 7. Business. In business and economics, these variables can be used to represent economic indicators, market parameters, or financial figures. For example, A might be the initial investment, B could represent sales revenue, and C might be the cost of goods sold. 8. Machine learning. In machine learning and data science, these variables can represent feature values, model parameters, or predictions. Understanding the significance of these variables is critical for model development and interpretation. In each domain, the specific meaning and importance of variables like A, B, and C depend on the context and the problem being addressed. Interpreting these variables correctly is essential for making informed decisions, solving problems, and gaining insights within a particular field of study or application. The concept of understanding variables and their significance is highly relevant and valuable in the field of AI architecture design. Here's how this concept applies to AI architecture. 1. Feature engineering. In AI and machine learning, features are variables that represent input data characteristics. Understanding the meaning and importance of these features is critical for effective feature engineering. Proper feature selection and transformation can significantly impact the performance of machine learning models. 2. Model design. When designing AI models, variables often represent model parameters, hyperparameters, and input data. A deep understanding of these variables helps in selecting appropriate architectures, example CNNs for image data, RNNs for sequential data, and tuning hyperparameters for optimal model performance. 3. Interpretability. In many AI applications, interpretability is crucial for understanding model predictions. Variables that contribute the most to model outputs need to be identified and explained. This is especially important in applications like healthcare, finance, and legal contexts. 4. Data preprocessing. Variables representing data preprocessing steps, such as scaling, normalization, and encoding, are essential for data preparation. Knowing when and how to apply these preprocessing techniques is key to model training and performance. 5. Model parameters. In neural networks, variables represent weights and biases. Understanding the role of these variables in the model's architecture helps in training, fine-tuning, and interpreting neural networks. 6. Hyperparameter tuning. Hyperparameters like learning rates, batch sizes, and dropout rates are variables that affect model training. A deep understanding of how these hyperparameters impact training dynamics is critical for optimizing model performance. 7. Loss functions. Loss functions are variables that measure the difference between predicted and actual values. Choosing the appropriate loss function depends on the problem at hand, and understanding their behavior is essential. 8. Data quality. Variables representing data quality and preprocessing steps are vital. Identifying and handling missing values, outliers, and imbalanced datasets are critical tasks in AI architecture design. 9. Scalability. As AI models grow in complexity and size, understanding the scalability of variables, including model size, computation requirements, and memory usage, is crucial for efficient deployment and resource management. 10. Ethical considerations. Understanding the variables related to bias, fairness, and ethics in AI is essential. Ensuring that AI systems are designed to be fair and unbiased requires a nuanced understanding of these factors. In summary, the concept of understanding variables and their meanings is foundational to AI architecture design. It impacts decisions related to feature engineering, model selection, preprocessing, hyperparameter tuning, and interpretability. A deep understanding of variables enables AI architects to build models that are both effective and aligned with the specific requirements and ethical considerations of their applications. Thank you.